Welcome back. So we have been looking at the Ramsey problem and how to solve the Ramsey problem using graph theory. So to recap, so what does the Ramsey problem say? So given two natural numbers p and q, we define the Ramsey number rpq as the smallest integer n so that among n people there exist either p of them who know each other or q of them who don't know each other. The idea is to prove that rp plus 1 q plus 1 is less than rp q plus 1 plus rp plus 1 q. And using this recurrence to prove that rpq is less than or equal to p plus q minus 2 choose p minus 1. Now, this second one is something that we have already done in our couple of weeks ago when we did induction on multiple variables. So, in this video, we would like to just prove this recurrence. Now, to solve this first recurrence, we would of course first try to understand this problem using graph theory. So let's see how do we model it in graph theory. We did it in last video. Let us quickly recap. So to recap, first of all we have the graphs, which is a set of vertices, a set of edges, and this is what the graph is given as, the set of vertices and set of edges. Now, if the relation between vertices is symmetric, that means if uv is in edge then vu is in edge, we call it an undirected graph. We can also have weights assigned to edges, and if there is an edge from u to v, then we say that v is a neighbor of u, and in an undirected graph the degree of v is the total number of neighbors of v. So pictorially, this is the set of vertices. The edges are drawn using lines joining the vertices. There can be weights on the edges, and there can be direction on the edges to represent the unsymmetric version of the edges. Right? In the last video, we also looked at some other properties or some other definitions on graph theory. In particular, we looked at the independent set and clique. So what is an independent set? So an independent set is a set of vertices such that no two vertices in this set has an edge between them. And a clique is just the opposite of it. Namely, a clique is a set of vertices such that between any pair of this set in this set there is an edge. Right? So, for example, if this is the graph that we have, A and E is an independent set. There is no edge between them. Similarly, B, C and G is also an independent set because there is again no edge between D and C and G and G and D. Right? Now, as a clique, we can have A, D, B is a clique because there is an edge between any two of them. Similarly, we can have A, D, B, E is a clique. Now, if we had an edge between A and E, then in that case, A, B, D and E would have been a clique also, because between any pair of between A, D, B and E there is an edge. Right? So we have an understanding of what an independent set is and what is a clique is. Now using these two notions, we can now visualize this problem. To visualize it, we have to understand what does it mean, and we have to first of all create a graph. So namely, let the people Bn vertices, V1 to Vn. And so this is the first thing, is to try to understand what does the RPQ imply. Right? We draw an edge between the vertex Vi and Vj if the person Vi knows person Vj. Now since person Vi knows person Vj implies person Vj knows person Vi, so the graph is an undirected graph because this relationship is symmetric. And what are we looking at? We want to find something like P people who know each other. So P people who know each other, meaning there are P vertices such that between any two vertex there is a edge. So that means there is a clique of size P. And similarly, if I am looking for Q people who don't know each other, or in other words, there are Q vertices such that between any two pairs, any pair of vertices in this set, there is no edge. So we get Q independent set. So if this is how we look at it, the definition of RPQ becomes RPQ is the smallest integer n such that the following can be told. Any graph on at least n vertices has either a clique of size P or an independent set of size Q. So this is how we would like to define RPQ. And what do we have to prove? So we note that Rp, 1 equals to R1, P, which is equals to 1. Because if you are given one vertex just, then there exists one independent set, so which is Rp1, and there is also one clique, so it's R1Q. So this note is easy to see, and we have to prove that Rp plus 1 Q plus 1 is less than Rp Q plus 1 and Rp plus 1 Q. Right? Now how do we prove it? The hint is we'll give a direct proof of it. So let's try to understand what we have to prove first. So this is the definition that we have. RPQ is the smallest integer n such that this following statement can be told. Any graph on at least n vertex either has a clique of size P or an independent set of size Q. Then we want to prove that this relation holds. So what we will show is that given a graph on n, this should be n vertices. Given any graph on n vertices where n is bigger than this RPQ plus 1 and RP plus 1Q, then there is either a clique of size P plus 1 or an independent set of size Q plus 1. Now why is this sufficient? So if we prove this statement, what do we end up proving? We're proving that the smallest n, the RPQ, is less than or equal to this plus RPQ plus 1 plus RP plus 1Q, which is exactly what we have to prove. Right? So what we prove is that if I give you a set, a graph, any graph with more than n vertices, but n is bigger than RPQ plus 1 and RP plus 1Q, then there is a unique, there is either a clique of size P plus 1 or a independent set of size Q. Right? So this is what is required to prove. So to prove this, let's start with a graph on n vertices where the n is bigger than what we just promised, is rp plus pq plus 1 plus rp plus 1 q. Now take any vertex v in the vertex set and consider the neighbors of v. So how does the graph look like? So here you have the graph G. Here you have a vertex V. Now there are some neighbors of V, right? So these are the vertices that have some edge to V. And then there are some vertices here that don't have any edge to V. So there are some vertices here and some vertices here. Vertices that are neighbors of V and vertices that are non-neighbors of V. So we call the vertices of V KV. We call it K because it's like the known. V knows this set of people. Remember that this graph is just a mathematical representation of the problem. And we will call the other one as NV. Right? So the set of neighbors of V is called KV, and the set of neighbors, vertices that are not neighbors of V are called NV. Now, given the fact that this n is bigger than or equal to this, we have two cases. First of all, either KV is greater than or equal to RPQ plus 1, or NV is greater than or equal to P plus 1, comma Q. Now, why are these two the only two cases? So, to prove that these two are the only two cases, what we have to see is that if neither of the case holds, then something wrong is happening. So, what happens if the first case doesn't hold? If the first case doesn't hold, then KV is strictly less than RPQ plus 1, which means it is less than or equal to this minus 1. Similarly, NV is less than or equal to RP plus 1, comma Q minus 1. Now, what is the size of the vertex set? So, this was of course n, which we started with, and this is, if you recall, it is the neighbors of V plus the vertices which are not neighbors of V plus the vertex itself, which is 1. Which is less than this plus this, which is RPQ plus 1 plus RP plus 1 Q minus 1 is minus 2, and then this plus 1, so I get minus 1. So, if neither of this case 1 and case 2 hold, then the number of vertices is less than this plus this minus 1. Or in other words, this is strictly less than. So, n is strictly less than this plus this, which is unfortunately not contradicting. Which is unfortunately contradicting this assumption that n is greater than or equal to. So, if case 1 and case 2 doesn't hold, we get a contradiction, and hence it cannot be that neither case 1 nor case 2 hold. So, either case 1 holds or case 2 holds, or maybe both holds, but both of them cannot hold is not an option. Thus, we get that we have get these two cases, namely KV is greater than or equal to RPQ plus 1 and NV is greater than or equal to RP plus 1Q. And what do we have to prove? If we can prove that in either case, either we have a clique of size p plus 1 or an independent set of size q plus 1, then what we have proved that we started with a graph G with n greater than this one, and we have proved that the graph either has a clique of size p plus 1 or an independent set of size q plus 1. And this is exactly what we wanted to prove in the first place. Right? So we will go by proving it case by case. So to start with, let's start with the first case, namely kV is greater than RPQ plus 1. Now let's look at what's going on before I start with the explanation. So here is the graph. Here was the set of kV. Here is the set of NV. And here is the vertex. Now every vertex in kV is attached to this vertex V. Right? Now this kV is bigger than this RPQ plus 1. What does it mean? If I look at just this graph, just the graph on kV, then we have these two options. This one, either kV has an independent set of q minus 1. That's what this definition of RPQ plus 1 means, right? Since kV is greater than RPQ plus 1, either there is an independent set of size q plus 1 sitting inside kV. In that case, that independent set is also an independent set of size q plus 1 there, right? For example, if this is an independent set here, that means no two vertex here has an edge between them, then the whole graph G, the whole graph is G, I still don't have any edge between them, and hence I get the same set of vertices is an independent set of size q plus 1 in G. Now, the definition that kV is greater than this, and the definition of RPQ plus 1 is either it has an independent set of size q plus 1 or it has a clique of size p. Now what happens if it has a clique of size p? Let's think of this blue thing again as a clique of size p. That means between any two edge here, vertex here, there is an edge. Now if this is a size p set, consider this set and this vertex v. Then this blue set plus this vertex v, we get a set of size p plus 1, and it is a clique between, because first of all any two vertex in this clique has an edge, and since all the vertices is subset of kV which are neighbors of v, so between v and any other vertex there is a clique of size, there is a clique, sorry, there is an edge, which means that this vertex along with this vertex v gives me a clique of size p plus 1. So either G has an independent set of size q plus 1 or a clique of size p plus 1. Now in case 2, we have a similar argument, except that now we will look at the NV setting. So in the case 2, the NV is bigger than RP plus 1Q. At this time, again, look at the induced graph on NV. Now since NV is bigger than RP plus 1Q, so by definition, two things hold. Either this will be NV, either this NV has a clique of size p plus 1, so either it already has a clique of size p plus 1, it's a clique here. In that case, this whole thing is still a clique of size p plus 1 in the original graph. And if not, The other thing is that the NV has a independent set of size Q. If it is an independent set, so if the blue thing is an independent set, what it means is that between any two vertex in this blue thing there is no edge. But then again, consider this blue with this V, and then we get this thing plus V gives an independent set of size V G plus 1. This is because this set now is completely contained inside NV, which by definition are the edges from which there is no vertex to V. Correct? So in that case also there is no edge. So in this case also we either get an independent set of size Q plus 1 or a clique of size P plus 1. So thus we started with this graph G, which has number of edges was greater than or equal to RPQ plus 1 plus RP plus 1Q. We picked up any vertex in V, looked at the neighbors and the non-neighbors. We had two cases and we proved that in either case, either there is a clique of size P plus 1 or an independent set of size Q plus 1. And hence we have been able to prove the Ramsey theorem. I mean, we ended up proving this recurrence relation. The fact that this thing follows from the recurrence relation, we did it a couple of videos earlier, actually a couple of weeks earlier. So again, we have seen how graph theory can be used to model a problem, visualize it correctly, and we solve it use graph theory to solve the problem. In the next video, we will be looking at graph theory. We will start looking at graph theory as itself and try to see how various properties of graph theory can be proved. So we'll start looking at some properties of graphs. Thank you.